All right, welcome back. We are now getting into how to graph acceleration. Before we learned that the acceleration formula was the change in velocity over our time. All right, which is important because when we graph acceleration, we need both of those concepts as well. So we have a velocity versus time graph. All right, so that's the title for our graph that we're drawing. And then we have our simple graph. We have time in seconds, and then we have velocity over here on our y-axis, and this unit is meters per second. All right, so here we are. Velocity is along the y-axis, so as something goes up, it is getting faster. As an object is going down the graph, it is getting slower. All right, and that depends on our velocity, which is on the y-axis, and so we can see the numerical values of that. We have just draw a couple of numbers in there just to give you that visualization of what is happening. And then we have our seconds. Just like that. All right. So velocity versus time graph, we have it completely set up now. Now, if we have, I guess one of the major questions that I ask and that is important is, what does the slope represent? So if our slope is our rise over our run, like we've mentioned before and time again, and we'll continue to do so, is our rise over the run. All right, first we check out our rise, which is velocity. And we check out our x-axis, which is our run, so that would be the time. Okay. And remember the units that we worked with before, like we have here. We have meters per second. All right. Does that ring any bells from the last video of a unit? If you have meters per second, that is the same thing as meters per second squared. All right, and what did we say meters per second squared represents? That's right, our acceleration. So on a velocity versus time graph, our slope is our acceleration. All right. Excuse me. So if we have an object that goes up to 1 meter per second in 1 second, then it goes just like this, has a horizontal line to it, and don't worry, I will come back to talk about things here. And then from 3 down to 4, it has a slope just like this. All right, so initially, what is our acceleration from here to here? Well, if you remember our formula, or you could just look at the rise over the run. So we have 1 meter per second over 1 meter per second. 1 meter per second over 1 second. So you have that, which will give us an acceleration of 1 meter per second squared. Okay, so there we are. At 1 second, we had a change in velocity of 1 meter per second, and so we're able to show that by this slope here. Now from this point to this point, let's look at things a little bit. Does our velocity change? It has a horizontal line, so it does not change along the y-axis. So our velocity is staying the same at this point. So you could say that it's staying the same. You could say that it has a constant speed. All right. Now let's calculate. Let's show you how it works in the formula to show you that it is a constant speed. All right. So what is our final velocity? Our VF. We have our VF minus VI over time. Remember, we need to write down the formulas before we use them. We have 1 meter per second minus our initial, which was 1 meter per second. And we see we got our VF because our VF was also 1 meter per second. And then our time was, we went 1 second, 2 seconds for this, so 2 seconds. Alright. Now you might say, well, 1 minus 1 is 0 meters per second, and we have 2 seconds here. Alright. And it's like, hey, you can't divide that because you have a 0 on top, and you're absolutely right. And so our acceleration is 0 meters per second squared. Alright? Because you cannot divide 0 by 2 to get anything. It's going to be 0. So you have acceleration of 0 meters per second squared, which is a constant speed. Alright? Because if you're not accelerating, you're not having a rate of change. So this just stays constant. And you see that by the horizontal line. It just stays straight across. Alright, now we have this section from 3 seconds to 4 seconds. And something's definitely happening here. So what is our final velocity? Our final velocity is here at the end, and you go to the 0 point. So if our VF minus VI over time equals, we said our final velocity was 0 meters per second. Our initial was 1 meter per second because that's where we started from right here to right there. And we have that, 1 meter per second. And the time that it took is from 3 seconds to 4 seconds, so that's just 1 second. And so if we subtract, we have 0 minus 1, we have a negative 1 meter per second divided by 1 second, which gives us negative 1 meter per second squared. So our acceleration is negative. Acceleration, right? Negative acceleration is what I'll put. Negative acceleration is negative 1 meter per second squared. And you also can see that since the slope is going down, you have a negative acceleration. Alright, so that's all there is to graphing acceleration. You have a positive acceleration if it's going up. If you're going straight across on a horizontal line, that is a constant speed, which constant speed you have 0 meters per second squared as your acceleration, because you're not changing anything, you're not changing direction, you're not changing the speed. And then from here to here, you have an acceleration of negative 1 meters per second, because remember, since you're talking about velocity and it's going down, so you have a not necessarily a negative speed, but you have a negative direction, alright, because velocity is both speed and direction. Alright, now since we brought up negative velocity, we'll continue on that trend and draw on the back of this. We have our velocity as our y-axis, because we're still doing velocity versus time. Versus time. Alright, now our scenario is this. We have an object, or our car, and we're going down the driveway, and once we get to the end of the driveway, we realize we left our wallet, we left the money back at the house, so we have to go back to the house. Alright, so as we're backing down the driveway, we have a negative velocity. Alright, now whether you want to draw that as as a constant speed or something that's accelerating, that is up to you. But for our purposes, I'm just going to say that we're going to talk about average speed, and we're going to talk about just a constant velocity. All right. But since we're going backwards, we have a negative velocity at a constant speed. All right. So this is us going backwards. I'm going to write backwards just so you don't get lost with where we're going. All right, so we go down and we get to the end of the driveway right here, and that only took us 5 seconds. It's not long. It's not a bad trip down the driveway. All right, and our velocity at this point in time was -4 meters per second. All right, not terribly fast, but fast enough to get us to where we needed to go. And then we realized we forgot our wallet at this point in time, and so it's like, oh man, I forgot it, so now I need to go forward. Well, you can think about this. You come to a complete stop. Say you stop for 1 second to put the car in drive. All right, and then so between 5 seconds and 6 seconds you're stopped. So you have a line right along the x-axis because you don't have a velocity when you're stopped. You're at 0. All right, and then from 6 seconds you returned to your house at the same speed, but now you're going in the opposite direction of that. So you find the quantity of your velocity, and then you just do this, just like that. Now realize that either this nor this, you have an acceleration, 0 acceleration, because we're just measuring the average acceleration. We're just measuring the average, and so we just found the average speed or the average velocity, and that's what both of these are.